All right, this is part 2, 5-4 gas laws and word problems. This will be a fairly short, I hope. I'm just going to work out the couple of calculations. So I showed you the concepts and the laws regarding the combined gas law, Charles law equation. This one is I had to do it in their class before I did this class. Okay, Boyle's law and Gay-Lussac's law. Okay, and combined gas law. Combined gas law. Okay, so I'm going to just do. I went through all the stuff, and then what you'll do. It's kind of better this way. As you do the problems, when you read a problem, it's going to be on the worksheet. They're all in word problems. You're going to have to decide, is it the combined gas law, Charles law, Boyle's law, Gay-Lussac's law? And you're going to have to plug in and get the right thing. Now, they're all based on this. So this kind of gas law problem is pretty easy to notice because usually it's like a before and after. Like it'll say, this was the pressure and the volume and temperature. Then we did something, and here's the new pressure was this, the new temperature was this, what's the new volume? So usually it'll be obvious when you go through them. Okay, so going back to 5-4, okay, there was one problem right there in 5-4, and it said, I think I remember this calculation, it's kind of an easy one, but we'll see. If a sample of gas occupies a volume, okay, so they gave me a volume. A sample of gas occupies a volume. Now, if you wanted to, you could just circle that where it says volume, but I'll say here, a volume of 200 cubic centimeters at negative 73.2 degrees Celsius, okay? Now, what is degrees Celsius? Is it P, V, or T? That is a T. I meant to ask you that. When you see the number, they don't always say the volume is this, the temperature is this. Sometimes it'll say a sample of gas, a 200 cubic centimeter sample of gas is at negative 73.2 degrees Celsius. It'll just say that. So you have to know, well, that's a volume, cubic centimeter, that's a temperature. Okay? Then it says, what volume would it occupy? So they're asking you for another volume at a temperature of negative 123.2 degrees Celsius. Pressure is constant. Okay, so that's obviously a temperature. So you notice they've given you a volume, a temperature, a volume, a temperature. So this would be like your initial volume at that temperature. They match V1, T1. V2, T2 would be your final. And we don't know the final volume, but we know the final temperature, and we know pressure is constant. So constant pressure would tell you that it's going to be Charles' law. But what you can do is start it off this way. Start with the equation. I guess I'll just put it all right here. P over V over T equals P V over T. This is not the problem that I thought it was going to be. Okay. So pressure is constant. So, okay, cross them out. So our law is going to be Charles' law. Volume and temperature are directly proportional. V1 over T1 equals V2 over T2. Now, next thing, first you ought to write down the equation. And that would be sufficient. You can write it that way. You don't have to write that one. You could, but I mean, that is the one. Well, what do they ask? What gas property remain constant? Oh no, I'm sorry. I'm looking at the wrong problem. That was one above it. Now, that's all you had to do. I recommend you always write the equation to start off. And that would count as the equation. Okay? A line through it means it's not there. I mean, if you really want to be better with it, you can do that. If you want to do it better, you can write that. That looks better, actually, I guess. So you might do that off to the side. You might just do the little cross out up here. And say, okay, that's constant. Oh, V2, V2. Okay, that's Charles' law. Now, an initial volume is 200 cubic centimeters. The initial temperature is negative 73.2, but what do you need to do? Can you remember? You have to Kelvinize that baby. So you have to add. Remember, Kelvin, they must have temperatures in Kelvin. And Kelvin is Celsius plus 273.15. Got to remember that equation. So I would not even write the wrong temperature there. I would never put Celsius in any of these gas laws, okay? So let's just take 73.2, and I'll even just do it right there next to it. All right, so plus 273.15 plus 273.15. And so, actually, that looks like it's going to work out to 200, right? 273.15. This is the problem I was thinking it was. Okay. So it's 199.9. Well, it's going to be 200 Kelvin. And that one is going to be 273.15 minus 123.2 is 150.0 Kelvin. So all I did was I changed this temperature and that temperature, which were Celsius, and I just now changed them into Kelvin. You can even do that right in the beginning of the problem if you want. So notice what T1 is equal to. It's 200 Kelvin. So that's why it's kind of a ridiculous problem when you see the math here. V2 we don't know, but we know that the of course we don't know V2. It doesn't go there. Yes, it does. What kind of craziness am I? I'm sorry, it does go there, V2. Okay, V1 over T1 equals V2 over T2. T2 is 150.0 Kelvin. Now, if you know a little bit about the math, you can say, well, if that's 200 and 200, that's got to be what? Okay, we know. Well, but what I'll do is the next step, first of all, right, first write the equation. Secondly, put in the number and the units, everything in the correct number and units. That can get you some partial credit, okay? Next, anything that you see twice, like Kelvin, Kelvin, crosses out. That one doesn't cross out because your answer will be in cubic centimeter. Then cross multiply. So 200 times 150 equals 200 times V2. So, the next thing to isolate V2, divide both sides by this. Some of you are thinking, like, why is he doing how easy this is? But I want to show you in case, because you're not going to usually have a problem that comes out this easy, you know. Divide both sides by 200 like that. And, of course, those will cancel out. Those will cancel out. Wait. What in the world did I just do? Crazy. 200 times 150 equals 200 times V divided by 200. Oh, okay. Yeah, I did. I've been a little bit ill the past days, and my head is headache, and I don't know. I guess I'm a little tired, but I'm getting better. But anyway, sorry. That is the answer. So 150.0 equals V2, and it's cubic centimeter. Oh boy. Yeah, it's so strange to see everything cancel, but as I said from the very beginning, 200 over 200 is what over 150? Well, that's 1, so obviously that's got to be 150. But anyway, that's the way you do it. Show the equation, show everything plugged in with the correct units, make sure you have Kelvin temperature. If you had different values for volume, make sure that if you had two volumes, like cubic centimeter, they both have to be in cubic centimeter, or both in liter, or both in milliliter, but just that's all you have to do. They would agree. All right, that is the problem A. And let me see what else. So twice I thought I made a mistake and I didn't, so I gotta just try to keep my mind hopefully a little sharper for this one. Okay. All right, here's another sample. Under Robert Boyle, there's a sample here. And I guess I might as well do all of these, okay? How much time is there? All right. If a sample of gas has a volume of 100, if you feel pretty good about it, you could jump to I tell you what, should I do that one first? Let me skip over to the combined law. Let me do that one instead. I'll go to the combined, I'll do that one. And then maybe I'll do that one at the end if you want to go back if you want extra practice. because I don't think we have to do all of these. They kind of get the, so they're all A, but this will be the A that's right under combined gas law. A sample of oxygen gas has a volume of 7.84 cubic centimeters. What is that? It's a volume. At a pressure of 540 mmHg. Do you know what that measures? Well, pressure. It says pressure there as well. They're not always going to say that. And a temperature of 25 degrees Celsius. Now, since I see 25 degrees Celsius, I'm going to immediately turn that into Kelvin. 273.15 plus 25 is 298.2. When you use the box rule, remember from long ago, 298.2 Kelvin. Now, why do I know that one so quick? Well, 25 is a temperature that you'll see later on. It's kind of understood to be room temperature. I better not say, I almost said a word that I didn't want to call it that because it will confuse you. And only you'll find out in AP later on one day what I'm talking about. But anyway, that's pretty much room temperature. Okay, now, then it says what will be the volume. So obviously you don't know another volume. If the pressure changes to 758 mmHg and the temperature is changed to standard temperature. Can you remember in the first video, standard temperature is always 273.15 Kelvin. It's equal to 0 degrees Celsius. So that one's pretty easy to convert. You're not really showing any work for it. Now, in the 1800s, they did not have refrigerating and thermostat systems like we do now. We could say, oh, set the temperature in the room to 20 degrees Celsius or whatever. So when they did a gas experiment, they wanted to make sure that they knew the exact temperature they did the experiment. So that if they told another person in some other country, some other place, whatever, if you're in somewhere else in the universe, whatever it would be, you need to know how to keep the same exact temperature. So what was an old way to do that, to be consistent, was to put it in ice water. In ice water, pure ice water, no, not salt water, just pure water with pure frozen water, ice. That would be exactly 0 degrees Celsius. All right. So I don't know if you knew that or not. When you make ice cream, you put ice and water, but you also put salt, which makes it get a little bit colder. But if you didn't put the salt, you just have ice and water, it would be 0 degrees Celsius. So that was a way to get standardized temperature. We don't really use that now anymore. The book talks about it. You'll hear it. You might hear about it a lot. But especially in AP, you're not going to hear them say that probably anymore. Okay? And you'll find out why in the next chapter, AP, a chapter that you will not be doing in General Chem. So, all right. Well, anyway, so here we go. That's standard temperature for this chapter. If you hear standard temp in the gas law chapter, it is 0 Celsius or 273.15. All right. All of that. Now, what we'll do is we'll go to our equations. And, oh, by the way, V1, P1, T1, V2, P2, T2. So here's the volume pressure at this pressure and temperature, and here's what will be the volume at this pressure and temperature. This tells you it's kind of like a before and after problem. So you go to the equation, PVT, and just plug them in. So P1, 540 millimeters of mercury. V1, 7.84 cubic centimeters. T1, 298.2 Kelvin. Sorry for this writing. It's the chalk and the angle. I'm starting to get kind of low on this thing. All right. What will be the, 758 millimeter of mercury. Volume 2, we don't know. And then the T2, 273.15. Now, okay, anything that you see twice, you can cancel out. Any unit. So show me the equation. And obviously, nothing is constant here, so it's going to be the combined law. So, let's see. Millimeter of mercury, millimeter of mercury. Kelvin and Kelvin. So cubic centimeter, again, we're trying to find volume, right? Yes. All right. So now we'll cross multiply, and I'm going to have to, I could use my little chair here too, I guess, couldn't I? Let me see. I didn't think about that, so I'm always trying to get down there so low. So 540 times 7.84 times 273.15 equals this top times bottom equals this bottom, this times this top, okay? Equals 298.2, times 758 times V2. Can I just reach? Okay, all right. So that will tell you the little algebra expression there. Now, if you wanted to, you could go and get the math, and yeah, I'll just do that. Or you could, what they do a lot of times in a, here I am, what they do a lot of times in a physics book, and probably maybe in your book too. We have a new book right now in Chem and in the AP book. They might do it the same way. They might just say divide this side by 298 times 758, divide this side by 298 in 758. So they could just do that, but I'll just go on and get the numbers. So let me go back here again. 540 times 7.84 times 273.15. It's really long. 1, 5, 6, 4, 0, 8. See, it's kind of a pain because you don't want to leave off a number or something. 2, 6, 0, 3, 6, V2. Now, I don't know if I would normally do it that way, but you can. And I'll also say this. Notice I didn't care about the sig figs right here, and you can do the same thing. Don't worry till the end. I know I'm way down. Like, where is he? Okay. Now I'm going to divide both sides by the number in front of V2. That 226036. 226036. So let me see if I actually get the right answer here. 1156408 divided by 226036. And I get 5.11 cubic centimeter. Does that show up on there even? It doesn't. Well, it will in a minute. 5.11 equals V2. I'm going to circle it, and I'll kind of bring it down a little bit so you can see. So 5.11 equals V2 from all that math. All right. So, sorry for shaking it around. Now, let me just try it again. So, on my calculator, I would say 540 times 7.84 times 273.15 divided by 298.2 divided by 758. It's 5.1. Well, I'll get 5.12 when I leave it all in, but 5.11, 5.12 will be okay. Now, the other thing, I did it without saying it. Since all you're doing is multiplying and dividing here, you can use the count rule. So just count 3 sig figs, 3 sig figs, 4 sig figs, 3 sig figs, 5. So 3, 4, 5, the smaller number is 3. So your answer is rounded to 3 sig figs. You don't have to round anything to the very end if you want. But again, show me the equation, show me everything plugged in with the correct units. Then do show me some kind of math. I mean, like, you can do some, you don't have to do everything that I did there exactly, but somewhere, if you show some math, the more you show, the better chance you might get partial credit if it's wrong. I think I mentioned in the last lesson, or if I didn't tell you, I grade these backwards a lot of times. Like, I'll look at the answer. If the answer's right, then I'll say, oh, did they show me the work? Oh, yeah, everything good. If the answer's wrong, then I go up here and I see, well, did they at least have the equation right? Did they plug in the things? Oh, they didn't change it to Celsius or whatever. So that's a very big error. If you don't change Celsius into Kelvin, I mean, that's a big one. But sometimes you might not get any credit at all if you did that. But well, in general, you might get some credit if you had the right equation at least. So okay, all right. So at this point, this is the hardest problem that you type of problem that you'll see in the work today. If you want to go right now and just do the work, you can. In the class, the general class, you're going to probably you might have more than one day to do this one. It might be a longer assignment. It might count as a double assignment. I'll just say it that way. But if you want to see one more problem, I'll do that other one that I skipped. But you can turn it off right now. You don't need to hear this. So I'll go back to the A that comes right before Joseph Louis Gay-Lussac right there. And it says also A, I should have changed it. If a sample of gas has a volume of 100 milliliters, when the pressure is 150 kilopascal, what is the volume? So we don't know. When the pressure is changed to 200 kilopascals, temperature and amount of gas are constant. Actually, in all of these, the amount of gas has to be constant. That just means no gas can escape from the balloon or from the can or whatever, the cylinder or whatever this thing's inside. It can't. It can't. If gas escaped or was added in, well, that would change everything. And we'll talk about that actually only in the AP class. You will not hear about that for the general. Well, you'll hear a little bit, but you won't have to do any math with it. I'll talk about it later. Okay, so whose law does this one look like? Temperature is constant. PVT. Temperature constant. Oh, okay, looks like Boyle's law, and it is. So P1 times V1 equals P2 times V2. So P1, now I didn't put, and if you say V1, P1, V2, P2, it doesn't have to be that V1 and P1 are the before and V2, P2 after. If you want to let V1 and P1 be after and P1 and V1, but that could be after, that could be before. It doesn't matter as long as you group them together. It was 100 milliliters at 150 kilopascal. That was grouped. What would it be? What would be the volume at 200 kilopascals? You could have changed the question and said something like the original volume was unknown, but we know the pressure was 200, and we know later the volume was at 100, and we measured the pressure at 150. Well, maybe I'm confusing you by saying all that. Let me just plug the numbers in and do it. So P1, V1. Just all I'm trying to say is the 100 on the equation has to go next to the pressure that it was paired with. If you put 100 there and then 150 over there, you'll get mixed up. P2 is 200 kilopascal. Get by. And then V2 we don't know. Okay. So, as I said, anything you see twice, you can cancel it out. So, get by. It's gone away. And now, 100 times 150 is 150,000. And 200 times V2. So now divide them both by 200. It's a lot easier math on this one. So 150,000 times divided by 200 is 7. Is that right? 750. 100 times 150 divided by 200. 75. Wait. 150,000 divided by 200. Wait, did I do something? Yeah, I did do something wrong right there. Aha. I didn't use my calculator, and I just put 150,000. It's not 150,000 because it wasn't times 1,000. It was times 100. So 15,000. Right. It looked a little bit weird. I always try to double check it, especially on the videos, because in class, usually people will say, hey, wait a minute, Bella. And it's always wise to be doing this along with me. If you ever find something wrong in a video, let me know. Let me know. But I think I usually catch them. Okay, so it's 75. All right, so that's going to cancel out. So 75. Now, for sig figs, how many? 3, 3, and 3. So it needs to be 75.0. And it's milliliters. And that should be volume. So it's great to do all these little things, putting in the unit. We know milliliter measures volume. Okay, I was solving for volume. That makes sense. If for some reason, it was like 100 and over here was like atmosphere or something, is V. It's like, wait a minute, atmosphere is pressure. So sometimes the unit will let you know that you're on track and have it right as well. Okay, so if that one helped you, you didn't have to see that problem too, but I wanted to just do it for extra example. All right, see you guys later.